In this lab, we were able to find the amount of excess charge on an ordinary object by applying knowledge of Newton's second law and third law in electric force. The goal was to find the amount of excess charge on one piece of charged Scotch tape. The purpose of this lab was to learn about charges and how they interact with everyday objects. This is a continuation of Lab 1, but uses a more sophisticated model for calculating the electric force on the charged tapes. In this lab, we used two charged tapes and the distribution of electric force that applies on one another to find the amount of charge on each tape needed for levitation. Because the system is in equilibrium, all forces have a sum of zero. Therefore, the sum of the electric force from the bottom charged tape and the gravitational force on the top floating charged tape equals zero. When two objects like the tapes are pulled apart, electrons are transferred. The range of excess charge that may be on the charged piece of tape is shown. Two pieces of Scotch tape were stuck together on a flat table and then ripped apart to create charged tapes. One tape was then hovered on top of the other. Then the magnitude of the charge was found using physics calculations. One tape was floated over the other. The distance between them was measured, and the force done by gravity on the top object was used to find the force of the repulsion on the top object. The physics properties applied are the following. Newton's second law, which is, at equilibrium, the sum of all forces in a system equals zero. The top tape is in equilibrium since it is not in motion, so the sum of the gravitational force on the top tape and the electric force on the top tape by the bottom tape equals zero. Then Newton's third law, which is, for every action there is an equal and opposite reaction. The two tapes exert equal and opposite forces on one another. Then the charge was determined by calculating the electric force from the bottom tape onto the top tape using the shown physics principle. Here are some more physics properties and equations used in Lab 1. In the first lab, the charges were treated as point charges. In this lab, the charges are treated as line charges. This new equation calculates electric fields that are better representative of the tapes and are more accurate and realistic. In the computational model, each tape is represented by multiple spheres. The top particle has two forces acting on it, gravitational and electrical, which equal one another in magnitude. The E-field function from Lab 0 was used to calculate the E-field of the bottom tape on the top tape. The point charge computed in Lab 1 was used as a starting point. Then the charge magnitude was increased until the charges allowed the sum of the electric force and the gravitational force to equal zero. Magnitude of the charge on one piece of tape was calculated to be the following. The link to the full code is included in the description of this video. In the screenshot of the computational model shown, the 10 spheres each represent each tape. The red spheres represent the top tape, while the blue spheres represent the bottom tape. The green arrow represents the E-field from top tape, the yellow arrow represents the gravitational force on the top tape, and the white arrow represents the electric force on the top tape. Here are some more data from the lab measurements and calculations. What was the magnitude of the charge on one piece of tape as calculated by your computational model? The charge I found was 2.7876 times 10 to the negative 8th coulombs. What assumptions, approximations, or idealizations did you have to make to determine approximately the amount of charge on the floating tape? This includes ignoring air resistance on a moving object, assuming that each U-tape had about the same amount of charge evenly distributed along the length of the tape, and that the tapes are placed directly above and below one another while levitating. What if you modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. The value using the point charge method was larger than the value using the line charge method. Why do these differ, and which value is more likely to be closer to the real value, and why? This is due to a difference in inaccuracy and accuracy between the two methods. The line charge model is more accurate and more likely to be closer to the true charge value, since the equation more precisely represents the physics that's occurring. On the other hand, the point charge equation is more simplified and generalized to represent the charge value.